And welcome back. We have been talking about the expansion of the universe. We've been talking about the age of the universe. We've been talking about cosmological redshifts, how as the universe expands, photons underneath it increase in wavelength. And that gives us an opportunity to relate those two things. The redshift, really, what does it tell us? It doesn't tell us how fast a galaxy is moving away from us. It tells us how much the universe has expanded since that photon was emitted by that galaxy. And that tells us the scale factor of the universe, how much the universe has expanded in that time. And that's directly related to the redshift z. The more a galaxy's photons have been redshifted, the more that light has been redshifted, the smaller the scale factor of the universe was when that photon was emitted. So this is a normalized parameter, the scale factor r. It's a measure really of how much smaller the universe was when the galaxy was emitted. R is 1 in the present day universe. At previous times, the universe was smaller, and so r was less than 1. And z, this RU tells us for a given galaxy how much smaller was the universe, what fraction of the size of the current universe was it when that photon was emitted, and we can tell that by how much the wavelength has expanded in the meantime, right? And here's the formula. RU is 1 over 1 plus z. So this tells us that at a given z value, what scale factor the universe was when that we're seeing for those galaxies today, when the photon was emitted from that galaxy long ago. It's a little confusing. Let me try to say that a little bit better. The scale factor tells us what fraction of today's size of the universe was when a photon left that galaxy that we're just getting now. Hopefully that was a little bit better. Anyway, let's do some examples and maybe this will be clearer. Let's do some examples. Here are some examples. 1, 1/4, and 9. Let's go to our whiteboard. So RU, the radius of the universe at some given z, 1 over 1 plus z. And our z values that we're going to use are 1, 0.25, and 9. Great. So let's do 1 first. RU equals 1 over 1 plus 1. That's 1 over 2. That's a half. So what does that tell us? It tells us that for a galaxy of z equals 1, we're getting the light now from that galaxy. But when those photons left the galaxy, the universe was half its present size. It has doubled in size in the time that it has taken that photon to go from that galaxy to us and be observed today. For z equals, that's the 1. For 0.25, RU 0 over 1 plus 0.25. Not 1, not 0, 1. And that is 1 over 1.25. You can do that on your calculator if you want. That's also 4 out of 5, 4/5, or 0.8, right? So the smaller the z value is, the larger the universe size was. And that makes sense. Z of 0.25, this galaxy is moving slower with respect to us. It's closer to us. The light has traveled a shorter distance. It has had a chance to expand less. And therefore, the universe was larger than this one at the time that it was emitted. Hasn't had a chance to expand as much. It was 80% the present size when those photons were emitted that we're just getting now from that galaxy. Z equals 9. RU equals 1 over 1 plus 9, 1 over 10, a tenth. For a Z equals 9 galaxy, and we're getting out to some of the most distant galaxies that we know of, The universe was only a tenth its present size when the photons that we're just getting now from that galaxy were emitted. Hopefully that explains it a little bit better than I did before. Okay. Back to PowerPoint. So, is everything expanding? Now, this is an interesting question. Is it that the stars within the Milky Way are expanding? Is it that the galaxies in the local group are expanding? Is it that the planets in the solar system are expanding? Is it the atoms in our body are expanding? It's a great question, and it's an interesting question. And the answer is, if that were the case, and this is interesting to think about too, if it were the case that everything in the universe were expanding at the same rate, including the atoms in our body and the atoms in the Earth and the atoms and the planets in the solar system, we wouldn't really be able to measure it. Because if your ruler is expanding at the same rate, and by your ruler I mean everything else in the universe is expanding at the same rate as your universe is expanding, you can't tell if the universe is expanding because everything is expanding with it. The truth is, it's not. The Milky Way is not expanding. The solar system is not expanding. The atoms in your body are not expanding. In fact, local gravitational effects can offset what we call the Hubble flow, the normal tendency for things, for space to expand between things. In fact, we know that this is the case because there are galaxies, specifically the Andromeda galaxy, that is blue shifted. It's actually moving towards us. So on small scale, some of these very nearby galaxies are clearly not following the Hubble law. And you can see that in other parts of the universe as well. Here is a Hubble diagram showing a nice straight line slope with lots of galaxies with a little bit of scatter. This is an observational scatter though. This is a real scatter. Some of these galaxies are moving a little bit with respect to their local space. And you're seeing that in this diagram. In fact, this very large distribution of galaxies in the middle here is the Virgo galaxy cluster. Why is this so much worse? Why is the Hubble law so bad here? Well, it's not really that the Hubble law is wrong. It's not really that we've measured the galaxy's velocities wrong. It's that when you get large numbers of galaxies in a small region, they tend, just like when you get large numbers of stars in a small region, they tend to be moving really fast around one another. The same is true of these galaxy clusters. They tend to be moving pretty fast relative to the normal velocity flow. So if you were to stand at the center of the Virgo galaxy, you'd say, yes, this galaxy cluster is at rest relative to the continuum, but look, there's galaxies moving this way and that way. It's sort of like a swarm of galaxies. And that, these galaxies all have about the same distance, but some of them have very disparate and different radial velocities, and that can spread things out in this direction. This is real. These are peculiar velocities, velocities that go against the Hubble flow, but it doesn't make the Hubble flow not there. It certainly is. And this whole center of mass of this galaxy is moving away from us at almost exactly the way you would expect it to, given its distance. The Milky Way isn't at rest. We know that there is a universal standard of rest, and the Milky Way is not at rest. We're moving towards the Andromeda galaxy, and the Andromeda galaxy and the entire local group is moving towards something that we call the local supercluster. And so these gravitational effects can affect things on small scales, independent of the Hubble flow, but on large scales, the Hubble flow always wins. Okay, I want to end this particular class by doing a couple of class actions with you to sort of hopefully get these concepts straight in your head, maybe better than they already are. So let's take a look. I need to share this with you. Okay. So let's do a warm up with an easy one. Ready? Here's Hubble's law. Which of these graphs correctly reflects the relationship between the recessional velocity v(r) and the distance for galaxies as expressed by the Hubble law, A, B, C, D, or E? I'll let you write down your answer. You can pause the video, think about it, look it up, and then we'll come back and talk about it. Okay, welcome back. Now you know that radial velocity and as a function of distance is increasing, right? The further you are away, the faster you're moving away. So that immediately eliminates C and D. D is not changing at all, and C it's moving in the opposite direction. So both A, B, and C, A, B, and E, you're getting larger velocities the further you get away. Great. Well, we know it's not E, it's a straight line. E is wrong. That looks like a rotation curve, but it's certainly not a Hubble law. So it's not E either. So it's either got to be A or B. Both of them have nice linear slopes moving away from the origin, but only one of these can be right. And in this case, it's B. How do we know it's B? Because it goes through the origin. We know that as you go towards distance equals 0, the velocity has to go to 0. It can't be that when you get to distance equals 0, there's still some positive radial velocity. That would not be a straight up consequence of some expanding universe. This is the only thing that can be explained by the expanding universe. And this is actually what we see. So it has to go to the origin. At distance equals 0, velocity, in fact, goes to 0. Great. Let's do another one. Let's do Hubble constant 2, Milky Way, and galaxy 1. Okay. The diagram below illustrates the velocity of galaxies for a Hubble constant of 70 kilometers per second per megaparsec as seen from the Milky Way. So you've got the Milky Way here, and you've got 4 different galaxies, 4 different other galaxies at different distances, and you're observing them at different velocities. So what would the velocity of the Milky Way be as seen from galaxy 1? What we see galaxy 1 at a distance of 10 megaparsecs moving away from us at a velocity of 700 kilometers per second. What would galaxy 1 see for the Milky Way? Think about it. Okay, commit to an answer. Here we go. What would galaxy 1 see for the Milky Way? Well, again, from the galaxy 1 standpoint, everybody's moving away from them. Galaxy number 2 should be 10 megaparsecs away and moving at 700 kilometers per second. Galaxy 3 is 20 megaparsecs and moving away from them at 1400 kilometers per second. What is the Milky Way? Well, we're 10 megaparsecs in the other direction, but we're also moving away from galaxy's 1 perspective in this direction. How fast? Well, same velocity, 700 kilometers per second in that direction, right? Galaxy 1 sees the Hubble law the same way galaxy 2 and the Milky Way do. The further away a galaxy is, the faster that galaxy will be moving away from that galaxy. Let's do one more here. We've got galaxy 4 and galaxy 2. So what would be the radial velocity of galaxy 4b as seen from galaxy 2? Well, again, all you have to do is subtract these numbers, right? Galaxy 4 is 20 megaparsecs away from galaxy 2, and subtract these two numbers. Galaxy 2 thinks they're at rest and sees galaxy 4 moving away from them at 1400 kilometers per second. And so the answer is 1400 kilometers per second. Okay, I need a couple more. Let's do universe age. Okay, this is a good one. I like this. Which of the Hubble diagrams below predicts the youngest universe? Again, this is a normal Hubble diagram, velocity versus distance, velocity versus distance, velocity versus distance. Which predicts the youngest universe? Again, think about it, pause it, come back, we'll talk about it. Okay, there's 2 ways to go about thinking about this. The first way is, remember what these things are. Let's take this one, right? At a given distance, this tells us how fast that galaxy is moving away from us. So at a given distance, this one is moving slow, this one is moving a little bit faster, and this one is moving fastest yet. Which is the youngest universe? Well, it's the universe that has gotten to this distance the fastest. Which one has gotten to the fastest? The one that's moving at the highest velocity, and that has to be this one. So just from a velocity, distance, time perspective, you can see B must be the youngest and A must be the oldest. The other way to think about this is to remember what the Hubble constant is. The Hubble constant is the slope of this line. So the Hubble constant is smallest in A and middle in B and largest in, middle in C and largest in B. And remember that the age of the universe is the inverse of the Hubble constant. The larger the Hubble constant, the younger the universe. So the steeper the slope, the larger the Hubble constant, the younger the universe must be. The answer is B. Okay, let's do one more. The local group. So how is the behavior of galaxies in the local group different from what we observe in distant galaxies? Larger fraction growing in size? No. Aging more rapidly? No. Some moving closer to us? Yes. This is the thing that never happens more near distant galaxies, but does happen in the local group of galaxies, particularly the Andromeda Galaxy. Several are rotating very, very rapidly. That's true, but that's no different than distant galaxies. The answer is C. Locally, some galaxies can disobey the Hubble law. Okay, we will stop there for today. We'll come back next time and talk about some other grand things in the universe, like dark matter. So come back then.